Hello everybody. Today's video lecture will cover atoms, molecules, and ions. This will be a two-part lecture, so the first video here will cover defining the atomic theory of matter, defining law of constant composition, the law of conservation of mass, and the law of multiple proportions. We'll also cover radioactivity, the atom, the nucleus, and subatomic particles, and then we'll also define atomic mass, atomic weight, and isotopes. That's probably where we'll end the first video. The second video will then cover reading and understanding the periodic table of the elements, defining what ions, polyatomic ions, and compounds are, and then we'll use nomenclature to write molecular formulas. So, let's go ahead and get started. So, some Greek philosophers back in the day believed that the smallest particle was this thing called atmos, or the uncuttable, right? And that's what made up all of nature. And so what that meant was that you would break down substances, whatever they can be, whatever they are, all the way down to the atomic level, right? And that's actually where the word atom comes from, atmos. And once you try to cut that divide that atom, that single atom, it no longer is an atom once you do that. So then in the 18th and 19th centuries, a whole bunch of different experiments happened, right? And it led John Dalton, who's the some people consider him the father of chemistry, right? It led him to organize his atomic theory based on a whole bunch of other discoveries, right, that happened. So the first one was the law of constant composition. The second was the law of conservation of mass. And the third one was the law of multiple proportions, which we talked about some of them already. So go ahead and log into your active and answer this question. Active answer number one. Or question number one, this is the way I'll be making sure that you're actually watching these videos. So go ahead and log in and answer that question. I'll have it open for you to answer. Moving on, so the first one that he based his atomic theory on was the law of constant composition. And what he said here was that compounds actually have a definite composition. What that means is that the relative number of atoms in each element of a compound always stays the same. If you had something like water, right, no matter how you divided the water or the H2O2, you'd always have two hydrogens and one oxygen, right? So this is what we call constant composition, right? Compounds will always be have the same number of atoms, number of each atoms, no matter how you divide them. Okay, so again, no matter how you divide the water molecules, it will always be H2O. If you divided anything more than that and it changed that, then it would no longer be water. This was discovered by a guy named Joseph Proust, right? And so this is one of the laws that Dalton actually based his one of his atomic theories on. The next one is the law of conservation of mass. And so another way of thinking about the law of conservation of mass is this: matter cannot be created or destroyed. Okay? So what that means is that whenever there is a chemical reaction that occurs, and you have the different atoms or the elements mixing together to make a new product at the end of the chemical reaction, the mass at the end of the reaction will be still the same as the mass at the beginning of the reaction, right? So that's the law of conservation of mass, discovered by a guy named Antoine Lavoisier. He was one of the very first real chemists, right, during the time of alchemy. A lot of his theories end up being correct, but he actually was executed by guillotine during the French Revolution, sadly. Next is the law of multiple proportions, right? And what the law of multiple proportions says that when you have two elements, say element A and B, combined with each other to make a new compound, right, they will always combine such that the ratio of B to A, right, will always be in small whole numbers, right? And all that means is that you can't divide an atom in half, right? You can't be like, half an oxygen atom, right, or half a hydrogen atom. It has to be whole numbers or whole atoms being combined with each other to make new compounds, right? So Here is the question number 2 for your active. Go ahead and log on, or if you already have it on, go ahead and answer that one. All right? Go ahead and answer that one. So now knowing all those three laws and what they mean, let's go ahead and put together the postulates of Dalton's atomic theory. The first of it, which is actually very obvious, right? But at the time it wasn't obvious. Each element is composed of extremely small particles called atoms, right? So if you have an element of oxygen or some oxygen in the room, right, it's all made of atoms of oxygen, right? If you have some nitrogen in the room, right, or element of nitrogen, it's all made of nitrogen atoms, right? Again, super obvious, but at the time it wasn't very obvious. I want you to take note of the fact that the oxygen here is red, right, and the nitrogen atom here is blue. All right, you'll need to know that for organic chemistry. Those colors are very important. They're the same everywhere. Also, if you have a black one, right, so if you have a black atom like that, that is always a carbon. And then if you have a white one, that is always a hydrogen. There are a few more colors, right? But those are the big four that you definitely need to remember. What does the second postulate say? Well, it says that all atoms of a given element are identical to one another in mass and other properties. But the atoms of one element are different from the atoms of other elements. Again, very obvious, right? But not obvious at the time. So if you look at a whole bunch of oxygen and you look at each of the atoms in that element of oxygen, right? That substance of oxygen, they are all oxygen atoms that are all identical to each other, right? But these oxygen atoms are not identical to nitrogen atoms, right? That are in the substance of nitrogen, or some nitrogen that's floating in the air, right? So basically, that says is that if you have a whole bunch of oxygen, all the atoms there will be identical oxygen atoms. If you have a whole bunch of nitrogen, all the atoms there will be identical nitrogen atoms. But an oxygen atom will not be the same as a nitrogen atom, right? Again, very obvious. The third postulate says that you cannot change, right? You cannot change a an oxygen atom, right, into a nitrogen atom using a chemical reaction. Okay, you cannot change an oxygen atom into a nitrogen atom using a chemical reaction. And then the last of his postulates says this, right? Atoms of more than one element combine to form compounds, which we knew that already. When you combine atoms from different elements together, they make two new compounds, right? But what the postulate says, though, is that the relative number and kinds of atoms will always stay the same, meaning that if you have a single nitrogen, and it combines with a single oxygen, it'll make this compound here called nitrous oxide, I think, right? I can't remember if it's nitric or nitrous oxide, but that's not important. It's the fact that the new compound also has one nitrogen. Sorry. Well, that's backwards. Whoever wrote this is This is backwards right here. So I need to fix that. Weird, right? This is the nitrogen. The N is the nitrogen right here, right? And then the blue is the nitrogen, and then the red is the oxygen. How weird is that? Wow. I didn't even make this. This came from my textbook. Oh, that one's right, though. Here we go. So anyway, back to what I was saying, though. If you have one oxygen, right, atom, right here, and it combines with one nitrogen atom, the resulting compound, nitric or nitrous oxide, I can't remember which one it is, right, the NO right here, will also have one nitrogen and one oxygen, okay? That is the fourth law, or fourth postulate of his atomic theory. So this is the third question right here. So feel free to, not feel free, but you need to answer this question on active, okay? Okay. All right. So, interestingly, though, Dalton, right, thought that the atom was the smallest particle, but that turned out not to be true. We know now today that atoms are actually made made up of subatomic particles, known as electrons, protons, and neutrons. So let's talk about them now, right? First, let's talk about the electron. So, What we have here is this thing called a cathode ray tube, right? Cathode ray tube. This is what old monitors used to be made of. Old monitors and TVs used to be made of, right? And you can see what's happening here is that there's electricity coming in on the side, right? And then there is electricity over here, right? And what happens is that there's a screen inside of the glass here, this cathode ray tube, and when electricity flows through it, it makes it glow or it fluoresces, right? So that on its own isn't super interesting. But what is interesting is that if you bring a magnet towards it, it actually makes the stream here, right, deflect, right? What that means then is that this particular stream is particles, possibly electrons, that are being affected by the magnetic field. So this discovery was a discovery made by a guy named J.J. Thomson, right? And he realized that that magnetic fields actually affect, right, the flow here of electrons. If you remember back in high school or maybe middle school, they always say electricity is the flow of electrons, right? Well, this particular experiment here shows that this flow can actually be deflected by magnets, right? So he did some more experiments, and he figured out that the mass to charge ratio, right, the charge to mass ratio of an electron is actually 1.76 times 10 to the eighth coulombs per gram, right? Coulombs per gram. That was the charge to mass ratio, right, of a electron. But he didn't know what the charge of an electron was yet, right? We know today, and you probably knew already today, uh, even before coming to this lecture, that electrons are negatively charged. But at the time, J.J. Thomson did not know that. You probably heard of J.J. Thomson before. I'll go back to it later, but he came up with this thing called the plum pudding model of the atom, where he had electrons just kind of floating around randomly in this mass, right here. They called it the plum pudding model. That's what he thought an atom was, and so I don't know what a plum pudding is because I guess that's a British thing, right? So I like to call it the chocolate chip cookie model. So you can just imagine that randomly throughout like chocolate chip cookie dough, right? The atom basically, there are randomly dispersed chocolate chips or electrons, and that was called the Thomson model of the atom. We'll talk more about that in a second. So Millikan actually was the one to discover what the charge of an electron was, and he did it using this oil drop experiment, right? So what happened was that he had this glass tube here, and then the glass tube, right, inside of it had two electronic plates there, electrical plates. One of it was negatively charged, and the other one was positively charged, right? He then sprayed drops of oil into the glass tube, and it started going into this hole, into this part right here in between, right? While it was in there, let me erase that real quick so you can see what's going on right here, right? While it was in there, he shot X-rays at it. So this is X-rays right here, shooting X-rays at it, right? And so those X-rays would give would make the oil drops to pick up electrons, right? And it would become negatively charged. And then what would happen when it became negatively charged was those negatively charged particles would start going towards or being attracted towards this top plate that was positive, right? Why is that important? The fact that that charge right there, the attraction between the negative and positive charge of the electrons being negative and this positive plate overcame gravity, because gravity would make these oil drops go down, right? But since he shot the oil drops with X-rays, it made them negatively charged, right? And they started migrating towards the positive plate, overcoming gravity, right? And so that's how he figured out that electrons were in fact negatively charged, right? Electrons are in fact negatively charged, right? They're in fact negatively charged. So here's the fourth question. Go ahead and answer that one on your active. So this is Marie Curie, right? She's a very famous scientist, very famous Polish descent, I believe. And so her and her husband actually studied this thing called radioactivity, right? She discovered an atom called radium, or discovered that radium was radioactive. It actually ended up killing her, right? I actually went to her grave. Uh, I think it's called the Pantheon in Paris, France. Her and her husband both died of radiation poisoning from radium, the element that they discovered, and the phenomenon that they discovered. And they were buried together in the Pantheon in Paris, France. Right. She did end up winning the Nobel Prize for this discovery. And so let's talk about what radioactivity is. So radioactivity is just the spontaneous emission of high energy radiation by an atom. Right. Atoms that can just sitting there can irradiate out energy. Right. Sometimes that energy is not bad. Right. But I mean, it doesn't hurt you, but sometimes it does hurt you. It's super high radiation. It can mess up your DNA. It can mess up your proteins, and it can cause cancer and stuff. And that's what actually ended up happening to Marie Curie. She was actually killed by the thing that she discovered. So, uh, whenever atoms are able to release energy on their own, they release them in the form of particles or rays, right? And so you have these things called alpha particles right here that are positively charged. They're not necessarily protons, but they are positively charged, and they're not dangerous. They don't hurt people, right? Then you have these things called beta particles. Same thing. They're negatively charged like electrons are, right? But they're not necessarily electrons. They're called beta particles. Atoms will release beta particles, and nothing really happens. And then they have gamma rays. Gamma rays are uncharged, and gamma rays are actually very dangerous, right? And so, how do you know? How did we figure out what the charge of these different particles are? Well, this guy named Ernest Rutherford came through, right? And he was able to get some radioactive substance and put it in this lead block right here. And the lead block had a hole in it, right, so that some of the radiation could come out. The radiation came out, and then he had two charged plates, and then he noticed that alpha particles, or let me start with beta particles, when they came through the charged plates, they were actually attracted to the positive plate. And then alpha particles were attracted to the negative plate, right? And so from that he deduced that alpha particles are positive and beta particles are negative because opposites attract. But then he saw that gamma rays had no charge because when they went through that plate, no deflection occurred, right? No deflection occurred. No attraction to either plate occurred, right? So that's how we were able to figure out what the charge of these different radioactive particles are, right? Gamma rays, bad. You know gamma rays are bad too because gamma rays are so powerful they can create the Hulk. So then now came the atom, right? Circa 1900, and I told you about this already, right? Where J.J. Thomson put forward this theory called the plum pudding theory, where he thought that electrons were negative, of course, right? But they were just randomly dispersed inside of an atom, right? Like so, these little blue dots, right? And then the positive charge would spread throughout the sphere of an atom. We know that's not true right now. Now we know that's not true. But again, I don't know what plum pudding is, so I just call this the chocolate chip cookie model. All right. So you can imagine then that each one of these blue things are chocolate chips, and they are randomly dispersed out through this dough, which is the positive charge throughout. Right. Then came along Rutherford again, right? The guy who discovered the charge of the alpha particle, beta particle, and the gamma ray, right? And he had this experiment called the gold foil experiment. Okay, he discovered that actually atoms did not resemble chocolate chip cookies, but in fact they had a nucleus inside of them, right? And so where there's a centralized positive charge. So how was he able to do that? Well, what he did was he had a source of alpha particles, as you can see right here, right? Oops, I'm sorry. Let me change that to a pen real quick. A source of alpha particles that he had right here, right? And these alpha particles will shot out a beam like that into some gold foil, right? That's why they call it the gold foil experiment, right? And when he did that, he noticed that some of the alpha particle beams got deflected, right? Some went straight through, right? And some of them just changed angles, right? So, what does that even mean? What does that even mean? Well, if you take a close look at this, right? If the atom was actually made up of what J.J. Thomson thought was just a sphere of positive charge, right? Then the alpha particle, remember that opposites attract and then like charges repel, right? Alpha particles, when you shot them at an atom, would just completely deflect back, right? They would just completely be repelled backwards, okay? But when he shot them through this gold foil, he saw that some of them went through like this, right? And then some of them got deflected like this. So the only way that could happen is if there were gaps in between the atoms, right? And from that, he was able to deduce that, in fact, neutrons, oh, sorry, not neutrons, the nucleus, rather, right? Or the center of an atom is where the protons are, right? And since they're in the center of the atom, and there's gaps between, some of the alpha particles can get through where they don't get deflected by the protons, but some of them actually hit one of the protons in the center of an atom and get deflected, right? So just from the gold foil experiment, he was able to discover that atoms are not in the form of a chocolate chip cookie, but in fact, atoms actually had a nucleus where the positive charge was, right? Where the positive charge was. And these positive charges sometimes deflected alpha particles because they were in the center of an atom when the alpha particle hit it, right? But sometimes did not because the gaps between allowed some alpha particles to pass straight through. And that's how you knew that these positive charges were localized to each individual atom in the center, okay? So let's take a closer look at the nuclear atom, right? So if you take a look at this particular atom right here, right? What you see here is actually this part right here is actually the volume of the atom that has electrons, right? That's occupied by electrons. And then this tiny little dot right there, right? This tiny little dot there is where the nucleus is, or where all the positive charge is, right? This is crazy, right? Because the entire atom itself, right here, this entire atom itself is anywhere between 1 to 5 angstroms, right? That's a very, very small unit, okay? We'll talk about angstroms later, but that's a very, very small unit, okay? But the actual diameter of the nucleus is 10 to the negative 4 angstroms, right? So that's like 0.0004, right? 1, 2, 3, 4 angstroms. So you can see how much smaller, right, a nucleus is to the actual atom itself, right? And how much more space electrons occupy than a nucleus does, right? Just to give you some more context, right? 1 to 5 angstroms is about 100 to 500 picometers. Oh, that's tiny, tiny, right? We're not talking like millimeters, centimeters. We're not talking about nanometers or micrometers. We're down to the picometers, right? Very, very small, very small. Okay. All right, so go ahead and answer this question, right? Go ahead and answer this question. All right, so let's put it all together. Okay, let's put it all together. We have 3 subatomic particles right here: the proton, the neutron, and the electron. Okay, we know protons have a positive charge, right? We also know that electrons have a negative charge, right? And then neutrons, which were in the middle, along with the protons in the nucleus, have a neutral charge, right? And so the joke I like to say to students so they remember what the charge of a neutron is: a neutron walks into the bar and asks, what's my tab, right? And then the bartender says, for you, no charge. Get it? Because neutrons have no charge. And then you can see here the respective masses of a proton, a neutron, and then electron. So the thing to note here is that neutrons and protons are actually very similar in mass, right? Uh, Almost a little bit more than one atomic mass unit, right? And then electrons are tiny, 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 right? They're to the -4, right? So again, that's like 0.0005486 AMU. So super small compared to a neutron and a proton, right? But they make up most of the volume of an atom, right? Because remember that protons and neutrons are all highly densely packed in the center, right? And then the rest of the space here, all around here, is where the electrons actually live, right? So, how do we determine which element an atom is, right? How do we tell which element an atom is? We do it by the atomic number, right? The atomic number tells you the number of protons, right? And that means that the atomic number and the number of protons tells you the identity of the atom. Meaning every different atom has a different number of protons, right? So if you have one number of if your atomic number is 1, or you have 1 proton, that makes you a hydrogen, right? If you have 2 protons, that makes you a helium, right? And so on the periodic table. So the atomic number or the number of protons identifies the atom. Okay? Changing the number of protons changes the atom. Okay? Another thing to note too is that atoms themselves overall have no charge, right? So the number of protons always equals the number of electrons, right? So then we can take a look at this particular notation here, where we have the element here is notated by a symbol, right? So here's C for carbon. And so when we write it like this, we have a number here, right? And this number here is what we call the mass number, okay? And the mass number is actually the number of protons plus the number of neutrons. And then we have the atomic number, right? And the atomic number is the number of protons. And again, the number of protons tells you the identity of the atom, okay? The identity of the atom, right? So interestingly enough, right here, if this is the number of protons plus the number of neutrons, right, and this is the number of protons themselves, what you can do is you can take this 12 here and subtract 6 for the number of protons that we have, right, and that gives you 6. So in this particular atom, which is carbon 12 right here, right, you have, I don't know why I wrote 16, sorry. You have 6 protons. You have 6 neutrons, right? And then you have also 6 electrons. Because in a neutral atom, right, the number of protons equals the number of electrons, okay? So the thing I want you to know, right, is, again, one more time, when you change the number of protons, that changes the identity of the atom. I'm writing too fast. The identity of the atom, right? So you change the number of protons, now you have a different atom. If you change the number of neutrons, though, right, that actually changes this thing called the isotope. We'll talk about that in a second. But just remember, it changes the isotope. Right? Still the same atom, but different isotope. And then if you change the number of electrons, that changes what we call the ions. The ion. And we'll talk more about that in a second as well, right? But I want you to remember that. Changing the number of protons changes the identity of the atom. Now you have a new atom, right? changing the number of neutrons changes the isotope, same atom but different isotope, and then changing the number of electrons, right, changes the ion, same atom but different ion. Okay, so let's go ahead and talk about isotopes. So what are isotopes? Isotopes are the same atoms, right, but with different masses. Different masses. Okay. Why do they have different masses? Well, because remember that the mass number, remember when we had this little notation here, right? This is the mass number right there. When you have the mass number, that mass number is the protons plus the neutron, right? Neutrons. If you change the number of neutrons, then the mass changes, right? So what are some examples of this? Well, we have some examples here of carbon. And you can see here, this is the normal carbon. 99.999% of all carbon atoms are made of carbon-12, which means that they have 6 neutrons and 6 protons. You could have a carbon-11, right? And here in carbon-11, you have 6 protons and 5 neutrons, right? So notice here the number of neutrons change, which means that you change the isotope. Another common one, or a common one, is actually carbon-13. More common than the rest, at least, the rest of the isotopes. Of course, carbon-12 is the one that's most abundant, the most common, right? Because 99.99% of all carbon atoms are carbon-12. But most of the rest is carbon-13, which has 6 protons and 7 neutrons. And then there's carbon-14, that has 6 protons and 8 neutrons, right? So does that make sense? When you change the number of neutrons, this guy right here, you change the isotope. So, go ahead and answer this question on your active. So next, let's talk about the AMU, or the atomic mass unit, right? We talked about the atomic mass unit a second ago already when we were talking about the different weights of the subatomic particles. But let's just remember, right, that atoms are extremely small, very small masses, right? The heaviest known atom, right? Single atom, by the way, heaviest known single atom is approximately 4 times 10 to the negative 22 grams. That is tiny, 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 tiny. Okay, tiny, very tiny, 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 right? So that's like 4, and I'm not going to draw them all out, but 4, 0 point, and then 22 zeros, or 21 zeros actually, sorry. 21 zeros, and then a 4 grams. That's so small. That's so tiny. You know what? I'm just going to write it out just so that we can see the scale here, okay? I'm going to erase that. And we're going to do that again here. So 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and then the 4. I might have miscounted there, but that's okay, right? Grams. So the heaviest atom, that's how much it weighs. Do you remember what I told you? I told you before. I may have told you this. I don't remember it, right? But a gram, you can think of a gram as being like a sugar packet. A sugar packet is about the amount of a gram, right? Right? So the sugar packet is pretty small. It's pretty light already. But imagine that. That is tiny, 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 right? So what is 1 AMU then? 1 atomic mass unit is equal to 1.66 times 10 to the negative 24, which is tiny, 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 right? Super tiny. So that takes us to talking about the atomic weight, right? Because in the real world, we use large amounts of atoms and molecules. So we use an average of all the masses, right? Mass calculations. What does that mean, an average of all the mass calculations? Remember back at carbon-12 right here, or the carbon one, the carbon isotopes? When we have carbon, right, as an element, a substance that we can use, we need to weigh it, right? And I'm not just talking about carbon. We're talking about anything like iron, gold. We need to weigh it, right? And so the atomic weight is actually an average of all the weights, right? Average of all the weights of all the different isotopes, right? And that's why when you look at the periodic table, if you look at the periodic table, most people will say that carbon has an atomic weight of 12, right? But it's actually not 12. It's actually 12.01, I think, right? I can't remember. I think it's 12.01. But it's not exactly 12, okay? It's not exactly 12. And so the reason why it's not exactly 12 is because we actually, when we in the real world, when we weigh out a amount of stuff, amount of carbon or whatever it may be, we actually use the atomic weight, which is an average of all the different masses of all the different abundances, right? So the atomic weight equals the sum, right, of the isotope mass times the fractional abundance, right, of all the isotopes, right? Okay, for all the isotopes. So the mass of any atom is compared to carbon 12, which is 6 protons and 6 neutrons, being exactly 12, right? So that's what we compare it to, okay? That's what we compare it to. All right, so there's this thing, right, that we use a lot in forensics called a mass spectrometer, okay? Most people know it as like a GCMS or an LCMS, right? Uh, so that stands for liquid chromatography mass spectrometry and gas chromatography mass spectrometry, mostly used in toxicology and drug chemistry, right, to see different poisons or drug molecules, right? But the thing that I want you to know about this, because you'll learn more about it when you get to a higher class, right, is a mass spectrometer can show you what the different abundances is of certain isotopes, right? So here we're looking at chlorine. And the two most common isotopes of chlorine are chlorine 35 and chlorine 37, right? Chlorine 35 and chlorine 37, okay? And so when you shoot like chlorine gas into a mass spectrometer, again, you don't need to know how it works, right? Because that picture down there is, how it works, right? You'll learn more about that later, I promise. But when you do that, it will show you chlorine 35 have this really tall peak right here, right? Which tells you how much chlorine 35 is there. And then you also have this other smaller peak, right? That tells you how much chlorine 37 is there. Those two different isotopes, okay? The thing I want you to note here is that chlorine 37 is only 1/3 the size, right, of the chlorine 35 peak, which means that gives you the relative abundance, right? For every chlorine atom, right, there are a third that are chlorine 37, right? So you have sorry, let me say that again. In a sample of chlorine atoms, right, there will be chlorine 35, and a third of those will be chlorine 37, right? A third of those will be chlorine 37. Okay. How interesting is that? That's super cool. If you actually go to, if you're a chemistry major or a biochemistry major, you'll be taking my class called Advanced Instrumental Analysis or Analytical Chemistry, or even if you take forensic science class with me, we'll talk a lot about mass spectrometry because that's what we use to identify unknown substances, right? All you do is you take off a little sample of the unknown substance and you stick it in the instrument, and the instrument will tell you what it is, which is super neat, right? Super neat. All right. And so go ahead and answer this question here, right? Go ahead and answer this question here, number 7. And then that will actually end it for this particular lecture, this part of the lecture. In the part 2, we will go over the periodic table. Thank you for listening, and I'll see you in class.